Hello, everyone. It's now 6:50, so we're going to start our lectures again. We're going to do 1 hour tonight, and hopefully you'll find it enjoyable. So I'm certainly aware that taking quizzes can be a rather trying experience, and so tonight what we're going to be going through is it's part of the workbook that's not actually there. It's an additional application section that I'm including. Now, what you might be happy to hear is that, roughly speaking, most of the content we're going to be covering tonight, strictly speaking, is not going to be assessed, at least not directly. Rather, the intention of this evening is to let you know how applicable all of the stuff we've been learning is to your future data science careers. So what we're going to do tonight is actually look at probability theory. The reason we're going to do that is because quite early on in Unit 9, I suggested that one of the reasons we needed to know integrals so well was because that they're essential to probability theory, and probability theory, I believe, is essential to statistics and data science. So we're basically going to treat this 1 hour lecture as an opportunity to see all of the great things we can do in probability theory once we have access to the integral. So let's get started. Usually when you deal with, when you start probability theory, you start talking about random variables and sample spaces. I'm not going to define random variables. I'm basically just going to assume that we're more or less comfortable with the idea of a random variable. Roughly speaking, a random variable is basically something that spits out a real number, and the real number is quite random. You can't really predict what it's going to be. So, for example, a random variable could be the number of heads you flip if you flip a coin 5 times, for example. So, a random variable is just a real variable that depends randomly on some underlying assumptions that we don't really have a good grip of. Okay, so hopefully I can assume that we're familiar with the idea of random variables. Random variables really come in 2 different types. Discrete random variables, where basically the real numbers come in discrete numbers. So for example, in the example I just cited, the number of times you flip heads if you flip a coin 5 times, that would be a discrete random variable because the only values it can have are 0, 1, 2, 3, 4, and 5. They're nice and separated. But really what we're going to be focusing on tonight is the idea of a continuous random variable. So when you say that a random variable is continuous, basically what that means is that there's a non-trivial probability that it can achieve a whole range, a whole continuous range of real values and not just discrete ones. But a bit more precisely, what we're going to say is that a random variable is continuous if it has a probability density function. So this is where we're going to start off, the definition of a probability density function. So the probability density function is a positive function f, so that basically what happens is the probability that your random variable lies between 2 numbers can be expressed as an integral. The integral is going to be from the real number a up to the real number b, and what you're going to be integrating is exactly this probability density function. So this is basically the reason why we need integration theory, because probability theory basically is, at least in the continuous setting, probability theory is basically the same as integration theory. So I've got a picture here to give you an idea of, roughly speaking, what's going on. So remember I said that this function f of x had to be positive. So we've got this positive function f of x lying over there. And what we're saying is that the probability that the random variable lies between these 2 values, a and b, this can be interpreted as the area under the curve of this curve f of x. The part of the curve is the part that lies between a and b. So this is what's going on, and you can see that Well, if the function f of x is bigger in a region, that means that the probability that your random variable lies between those two numbers is quite large. If the area is small, if the function f is small, then you would expect the probability theory to be much lower. Now, question for the audience, please. Before I do that, we've got a question. Isn't it CDF instead of PDF? No. We're going to discuss both the probability density function and the cumulative density function quite soon. They are related, but they're not exactly the same. So hopefully, we'll get to CDFs later. Please ask me again if it's still unclear. But for the moment, we are actually just dealing with probability density functions. Okay, so you're pointing out that you think this PDF, are you talking about this graph here? So the PDF is, I guess to some extent you're right. I mean, the PDF is just the function f of x, whereas the CDF, that's formed from integrating, but we'll define that a bit more carefully later. Yeah, so we'll discuss CDFs quite soon. I'll get to that in a second. Okay, now I've actually got a question for the audience before we get into CDFs. In fact, this might be one way to segue into the definition of the CDF. What is the integral from minus infinity up to infinity of f of x dx? So this is saying we've got a probability density function f, and it's positive, remember. So what the question I have for you, okay, I've already got the answer. Yeah, the answer is 1. The reason the answer is 1 is because, well, if we're looking at the integral from minus infinity up to infinity, then that's the same as the probability that x is between minus infinity and infinity by definition. But by definition, also, we're saying that x is a real number. So there is a 100% chance that x is between minus infinity and plus infinity. So that means we have no choice. The only functions that can be probability density functions are those that integrate to 1. Another way of seeing this is that there is a 100% chance that x is a real number, but of course that's true because that's the definition of a random variable. So this is their definition of the probability density function. But by definition of the probability density function, it has to integrate to 1. Okay. Now, there's another interesting point to make. The probability, if you have a continuous random variable with probability density function f, then the probability that x is equal to a specific value, so that's the same as the probability that x is greater than a and x is less than or equal to a, well, more or less by definition, this is equal to the integral from a up to a of f of x, but by our convention, this integral is going to be 0 no matter what a we pick. Now, this is an interesting fact about continuous random variables. The probability of your random variable being equal to a specific number, that's actually always going to be 0. So for example, if you think that if your random variable is pick someone at random and measure their height, and you might ask, how likely is it that the height that you get is exactly 160 centimeters? Well, the answer is 0%. There is a 0% chance that they have exactly 160 centimeters in height. It could be 160.1, 160.001, and so on. It doesn't really make sense to ask how likely it is that the random variable is equal to a specific number because it integrates to 0. Rather, what we have to ask is how likely it is that X lies in particular non-trivial ranges. So this is the idea behind probability density functions. Okay, an example. Let's say our random variable comes from the following random experiment. We basically just pick a real number from the interval from 0 up to 2, and we do it uniformly and at random. And the question is, if X is the real number selected, so that's our random variable, what is its probability density function? So I was thinking maybe I would ask the audience what they think the answer to this one is, but I suspect maybe you're all a bit tired, and I won't push this one. I will just tell you. The answer is this. Now let me try and explain why. So that what I'm saying is that the probability density function is going to be a half if X is between 0 and 2, and it's going to be 0 otherwise. Now, why is this the case? Well, let's draw this function to see what's going on. Let's put 0 there and 2 there, and let's put a half there and 1 there. Oh, sorry. Our function basically looks like this. And then, oh, I got it wrong again. It's supposed to be at a half, and then it hugs 0 for the rest of the way. Now, why is this the probability density function? Well, let's check. Let's check that this actually works out. What happens if we're looking, the question is, what happens if we're asking about how likely it is that X is less than 0? How likely is it that the real number we select is less than 0? Well, I mean, this is equal to the integral from -infinity up to 0 of f of x dx. But X is 0 here, so this is defined to be 0. But this is exactly what we want, because we're told that we're only picking real numbers between 0 and 2. So there should be no chance that we select a number less than or equal to 0, because that's how we've defined this experiment. And similarly, that's why this function has to be 0 over here. Now, the next question is, well, why should it be a value of a half here? Well, basically two reasons why. The first is that we need this area under here to be exactly 1. And indeed, it is the case here, because 2 times a half is exactly 1. Now, the next question is, well, fine, but why couldn't you pick some other random curve that integrated to 1? Well, the answer is because I'm asking for a uniform selection. And while from the question itself, it's a bit unclear why this needs to be a straight line, this is more or less what I mean by this word uniformly. Means that PDF must be constant on 0, 2. I mean, to be a bit more precise about what I mean by the word uniformly, what I mean is that the likelihood of selecting a number within a particular sub-interval of 0, 2, that should only depend on the length of the interval and not where that sub-interval is actually located. Yes, so this is that particular example here. So I'm just trying to make sense of the comments here. I might move on for the moment. If you have more questions, please let me know. But it's a bit unclear what's being said in these comments here, so I'll just move on for the moment. Okay, we'll now get on. Oh, sorry, yes. Before we move on, let's just point this out. It's important to note that the integral of the probability density function is 1, and that's because the integral of a half from 0 up to 2 is exactly 1. Okay, now we're in a position, I believe we're now in a position to talk about the cumulative distribution function. So we were talking about probability density functions before. Density is an interesting word because roughly speaking, it means whenever you talk about densities, that means you have to integrate a density to get an actual value of something. And this is the key. This tells us how we go from the probability density function to the cumulative distribution function. So while the probability density function gives us an idea about infinitesimally how likely a particular value is to occur, the cumulative density function, the cumulative distribution function actually works out probabilities, and it does so by integrating. So by definition, just the definition at this stage, if you've got a continuous random variable, then its CDF is the function capital F that goes from the real numbers into the interval 0, 1. And we have that f of x is defined to be the probability that the random variable capital X is less than or equal to x. Now, of course, the reason that the range of f happens to be the interval from 0 up to 1 is because, well, by definition of probability, the probability of anything occurring has to be between 0 and 1. So that's why this interval is that. Now, the next thing we need to talk about are properties of this cumulative distribution function. So first and perhaps most importantly is the fact that this function is actually increasing. The probability that f of x is less than or equal to f of y whenever x is less than or equal to y. And I think this makes lots of intuitive sense. The reason is that, well, I mean, if x is less than or equal to y, then the event x being less than or equal to x actually implies that x is less than or equal to y. So surely then the probability that this occurs has to be less than or equal to the probability that this occurs, because it's much easier for this event to occur than it is for this event to occur. And so that means that this function is an increasing function. The probability that capital X is less than or equal to x, that increases as small x increases because it's much easier for that random variable to stay below that particular number. Now, putting this increasing idea of f to the extremes, we can see what happens if we push x all the way to plus infinity, and we can try and see what happens when we push x all the way down to minus infinity. And maybe you can guess what goes on here. If we push x all the way to plus infinity, then this cumulative distribution function is supposed to approach 1. And this makes a lot of intuitive sense as well, because if you push this number to plus infinity, well, we're looking at the probability that the random variable is less than or equal to x, and we're making x really, really large. It's supposed to be really easy for that random variable to be less than a really large bound. As we push that bound to its limits, we get 1, because we should, as we make x really large, we should be becoming almost certain that the random variable is indeed less than or equal to that upper bound. On the other hand, if we push x to minus infinity, then we're looking for the probability that the random variable is less than a really, really small number. The smaller we get, the harder it is for the random variable to be bounded by that. And so we would expect that the probability becomes negligible. The probability should shrink to 0 in that case. Now, the final property of the CDF is the one that unites all of the theory of derivatives and integrals that we've seen so far, and also links the probability density function to the cumulative distribution function. The relationship comes to us from the fundamental theorem of calculus. The CDF that the cumulative distribution function is always continuous, and it can be found by integrating the probability density function from minus infinity up to x. Therefore, so this tells you how to find the cumulative distribution function from the probability density function, and the fundamental theorem of calculus tells us how to go the other way around. If we've got a cumulative distribution function, how do we find the probability density function? Well, if we just apply the fundamental theorem of calculus to this equation here, we find that the probability density function is found by taking the derivative of the cumulative distribution function. And the reason for that is basically the one we've been emphasizing all along, that integrals are in some sense the opposite of the derivative. If you integrate to go from PDF to CDF, then you should be able to differentiate to go from CDF to PDF. Now, I hope that shed some light on the relationship between these two objects now. We're now going to have a look at that example we just saw, but in the context of not just the PDF, but the PDF and the CDF. So same question as before, draw a number from the interval of real numbers from 0 up to 2, uniformly and at random. Find the cumulative distribution function, capital F, hence find the probability density function. Now, we actually already found this in that previous question, but this time we're going to take a slightly different route. Okay, now what is the cumulative distribution function going to be? Well, there's basically three cases we need to consider here. Remember, f of x, let's make this a bit cleaner. F of x is equal to the probability that the random variable is less than or equal to x. If x is less than 0, f of x has to be equal to 0 because we're only drawing numbers from 0 up to 2. There is no chance, by definition, there is no chance of drawing a number that's less than 0. And so the probability that our random variable is less than a negative number is 0. That can't happen. On the other hand, if x is bigger than 2, f of x has to be equal to 1. Because there is a 100% chance that the number we select is between 0 and 2, because that's just our definition of our random experiment here. And so there is a 100% chance that our random variable is less than or equal to 2. So what have we got here? We've got, if this is our CDF here, and this is 0, and this is 2, and we've got 1 here and 0 here, it starts at 0 and ends at a flat 1 here. What goes on in between? Well, it's again the word uniformly that helps us here. That the fact that it's a uniform randomness means that this really has to be a straight line here. So this is a graph of the cumulative distribution function. More concretely, this is a much cleaner way of actually writing it. As I just suggested, f of x is equal to 0 if x is less than or equal to 0. It's equal to x on 2 if x is between 0 and 2, because that's the straight line function that joins 0 to 1, and 1 is the value it takes if x is greater than or equal to 2. Now, we're not done with the question yet. We're told to hence find the probability distribution, the probability density function. Now, the thing that's important here is that this function f of x is not actually differentiable everywhere. Because remember, it has corners here and here. This function is not differentiable here. It's not differentiable at the value 0, and it's not differentiable at the value 2. But everywhere else it is differentiable, and we differentiate. And remember, f of x is defined to be the derivative of the CDF. And so, well, if we differentiate a constant, we get a constant. If we differentiate a constant, we get a constant. But the derivative of x on 2 is precisely equal to a half. Well, that's great because that's exactly the same probability density function we had previously. Now, I thought it'd be handy to show you, well, we've already seen what these looks like, but I managed to do a TIX drawing of what these guys actually look like. So as I pointed out before, the CDF starts at 0, increases, and then goes to 1, whereas the probability density function starts at 0, jumps to a half, and then goes back down to 0. Excuse me. So we've got a request here to explain why the cumulative distribution function is 1 if x is bigger than or equal to 2. So let's have a look at this. So the reason is, so if x is our random variable, x is the random number in the interval 0 to 2, by definition almost, x is always going to be less than or equal to 2. So this is always true. So therefore, the probability that x is less than or equal to 2, this is 1, which is 100%. Because if we're looking at the probability of an event occurring that we know must always occur, well, that has to be 100%. There's no way around that. But of course, this is exactly equal to the function f of 2. So this is why f of 2 is equal to 1. And you might wonder, well, why? That's fine, but why is it true that f is 1 for any value bigger than that? Well, if x is bigger than or equal to 2, then it's still true that x is less than or equal to x by definition. Because if x is less than or equal to 2, it's definitely less than or equal to small x. And so once again, we have that this is equal to 1. So I hope that cleared that up for you. And yes, as Zhao Wang has pointed out, a rough shorthand way of describing this idea is to say that the derivative of the cumulative distribution function is indeed the probability density function. All right, so this is the bread and butter of probability theory: random variables as well as functions which determine their probabilities. Now, what do you want to do with random variables? Well, in statistics, what you like to do quite often is find the mean. If you've got a data set, you might like to find the mean. In the language of random variables, finding the mean is basically the same as asking about the expectation of something. So we can talk about the expectation of a random variable. So let's suppose that you've got a continuous random variable with probability distribution function f. So pick any real value function g. Now, if x is a random variable, then g of x is another random variable because its input is random. And by definition, the expectation of g of x, which is another random variable, is given by the integral from minus infinity up to infinity of this g of x function multiplied by f of x. So what's really going on here? The expectation is basically a best guess at what the mean of a random variable should be. So if we take data points, so if we just apply this random variable a number of times and the data we get is x1 up to xn, then the expectation of g of x, basically the way we define the expectation means that this particular number, the expectation, this should be close to the mean of these numbers here. So the idea is that if some values come up much more than others, then if we do this experiment a number of times, we should see that number come up. And so that should be close to the mean there. So one can think of the expectation as a sort of average, the average value that g of x achieves, but you have to be careful. You have to weight the average according to how likely these values are to actually occur. So this is the expectation. Let's have a look at an example. So this is sort of an electrical engineering computer science type question. Let's suppose that you've got a signal. Let's say that well, roughly speaking, we want signals to just be a basic trigonometric function. We want them to be a times cosine over omega t, but maybe we've got some randomness in the phase here. So let's chuck in some randomness. Now, it turns out that for whatever reason, we know that this random variable x, it lies in the interval 0 up to 2 pi, and it's uniform. So that's a good assumption to make. What you need to do is find the expected value of the signal of find the expected value of y. So that's denoted with this e, the expected value of y. Now, when you're looking at these sorts of signals, y is, I guess, the amplitude of your signal. But if you square it, if you're an electrical engineer, you might be aware that when you square these things, that tells you how much power is going through this system here. So find the expected power of this particular signal. Now, the way we need to do this question is first we need to find the PDF of x. Now that we've seen some examples, maybe I'll invite audience participation again. Can you put in the chat what is the PDF of this random variable x? I'll give you I'll pause and let you construct your answers if you can. So that's almost there, Xiaowang. You've got to be a bit careful because when you're defining a function, remember the PDF is a real valued function. So you've got to tell me where it's equal to 1 on 2 pi. So I'll probably just get on with it. So like was suggested in the chat, the function is really 1 on 2 pi, but this is only if your x is in the interval of interest. Looks like I've been a bit careless here. I've switched my intervals around. It doesn't really make much of a difference, but I guess it's good to be consistent. So that's a bit sloppy. Now, the important thing to know is that this function has to be 0 otherwise, because by definition, this phase lies between 0 and 2 pi, and so there's no chance of getting any other value. So this is the probability density function. Now that we have the PDF of x, we're basically good to do a whole number of computations here. In particular, we're now in a position to calculate the expected value of y. Now, by definition, the expected value of y is equal to minus infinity up to infinity of, well, basically we look at the definition of y and put it down here, but every time we see a capital X, we have to replace it with a small x. We also need to multiply it by the probability density function of x, and we integrate with respect to dx. But remember, this function is 0 unless we're in the interval 0 to 2 pi. So that means it suffices to do this integral from 0 up to 2 pi. And that's exactly what's going on here. Now, because we paid attention in class last week or the week before, we know how to integrate the cosine function. The cosine function just integrates to sine. Now, it's important to note that we're only integrating with respect to x. We're not integrating with respect to omega d. So when we do this integral, I won't do this computation, but you get sine of omega t plus 2 pi minus sine of omega t plus 0. They cancel out because sine is 2 pi periodic, and we get 0. So this is interesting. Even though we've got some randomness in the phase here, the expected value of the amplitude of this signal is still 0. This doesn't always happen. The reason it happens this time is because we're assuming uniformity of the randomness. This wasn't the whole question, though. We also have to do a bit of a more tricky integral. We needed to calculate the expected value of y squared. Now this is equal to minus infinity up to infinity of the probability density function times this, but now we have to square it. A cosine, I won't put the input of the cosine there, squared dx. So I've got to square everything this time. So this is the integral this time. Now it's actually a bit of a trickier integral to do. Integrating cos squared is not, I don't think it's obvious. The way to integrate cosine squared is to use one of your double angle formulas for cosine and sine. Cosine squared is the same as a half plus a half times cosine of twice whatever's in there. You might recall that identity from high school or somewhere else. But now we're in a position to integrate this. Same thing as before. I find an antiderivative for cosine, that's sine. An antiderivative for a half is just x on 2. The a squared comes out the front. And this is the expected power there, a squared on 2. So this is saying that on average, a best guess as to where most of the data is going to be, or a best guess of the average of all the data is going to be a squared divided by 2. Okay. Another thing we have to talk about with random variables that's very important is variance. So given a random variable, what we seek to do is to produce numbers which give some meaningful description of the behavior of the random variable. The expectation is one particular example of a number we can associate to a random variable that describes what the random variable looks like. The second most important one, some people might disagree, but I would say that the expectation is the most important summary of a random variable. I would say that the variance is the second most important piece of information. Can't spell. Piece of information. Okay. Now, we've got a technical definition of variance here. It's the expectation of a new random variable. This new random variable is found by taking the old one, subtracting the expectation, and then squaring it. While that's technical, I'll aim to not go into the technicalities too much, but it is important for you to know that the word variance was not just randomly selected. It's because this number here does actually measure how spread out this random variable is. So roughly speaking, like if you had a random variable x, and the probability density function looked like that, then you would say that the variance is high. Whereas if you had a random variable whose probability density function was like all of the data was in one particular point, then you would say that the variance is quite low because there's not really much spreading out going on. If you do this experiment, most of the time you're going to end up pretty close to there. Okay, so now expectation and variance, they're quite important things to look at. Now, before moving on from the definition of variance, there's something else I want to point out to you, and it's that you will have actually seen the variance before. It's this idea of the standard deviation. In fact, the relationship is quite close. If you take the variance, sometimes you will denote that with sigma x squared, and this number sigma x is called the standard deviation. So if you know what the variance of a random variable is, then the square root of that variance is called the standard deviation of x. I suspect you all would have come across the notion of standard deviation before. Okay, so that's the definition of variance. Now, I'm going to list, whenever you introduce new theory, it's good to see what properties your theory has. And we're going to do that now. Properties of the expectation and properties of the variance. So it's quite similar to what we saw for integrals and derivatives. Now, in these slides, I do actually have a solution to these questions, but maybe I won't go through them in great detail. So it turns out that if you have a random variable x and you have two real numbers, you scale x by your number a and you add b to it, then this is the same as multiplying the expectation of the original random variable by a and simply adding b. I guess this makes sense because if you take a random variable and simply add 1 to it, then you would expect that the expectation would be 1 more than what the original expectation was. And similarly, if you scale something, you would expect the expectation to scale similarly. And you also have this property. If you're looking at functions of random variables and you're adding those random variables up, then the expectation behaves similarly. So the way we can roughly describe this is that the expectation is linear because it satisfies the sort of linearity properties that we've come across before. On the other hand, the variance behaves a bit differently. It turns out that a nice way of describing the variance of a random variable is by taking the expectation of that random variable squared and then subtracting the expectation squared. So these are not the same thing, so they don't cancel out to give 0. Another property is that if you scale your random variable by a number a and add b to it, then the new variance is a squared times the old. Now, one way of describing this is by saying that variance is basically a quadratic function, because if we put a inside, then we get a squared outside. Now, the other question you may have is, well, what happened to b here? If we had b here, how come it's disappeared over here? And the reason is quite intuitive. It's that if you take a random variable and you shift it, you're not actually changing how much it's spread out. You're merely relocating all the data. And since variance is a descriptor of how spread out the random variable is, shifting it to the left or to the right shouldn't actually affect anything. So one can say that variance is quadratic, and that's one way to describe the properties of variance. Now, I might skim through the next few slides. We've got a comment here. Could you elaborate on that comment at all? Was that along the lines of what I was just suggesting, or is there something else that you'd like to mention there? So you're still talking about the variance there, or are you talking about the expectation? You're talking about the variance. Yes. Okay. Yeah. So I guess the reason is more or less along the lines of what I just suggested. If you shift everything by b, that doesn't change how much it's spread out. It merely changes where the data is centered. Okay, so in my slides here, we've got the proof of these results, and the proof is basically just playing with integrals. I probably won't go through the details because they're a bit intense, but maybe if you're interested, you can peruse these in your own time. So what we have to do is play with the definition of expectation, use the definition of expectation, use the linearity of the integral. basically this slide is just a consequence of the linearity of integrals. So basically everything that's in this slide comes down to the fact that integrals are linear. Now, on the other hand, the variance is a bit more interesting. You have the definition of variance. It's defined to be this. We expand the square there. We use the fact that the expectation is linear to get this. So that's why the variance looks like that. Now we also have to check that other property we had. If we scale and shift by A and B respectively, what happens? Well, we just continue through. It's just basically playing with the definition of integral and the properties of expectation that we'd already established. So I won't go through this because I think it's a bit heavy for tonight. Instead, what I wanted to get on with are actual examples that you're likely to see in real life. So I'm going to skip all of this and get on to some examples that you might come across in real life when you're doing data science. Now, the first one is one we've actually seen a number of times now, but it's good to start with what we know. The first example of a distribution is the so-called uniform distribution. If you have a random variable x, you say that it has a uniform distribution on the interval a up to b if it has a probability density function, and the probability density function looks like that. So what's going on here? What we're saying is that this random variable only picks values on the interval from a up to b. And so the probability density function is going to be 0 everywhere else. And the probability density function between these values is 1 divided by b minus a. And that's so that this area here is exactly 1. So this is the uniform distribution. This is actually something we've seen a number of times now. But now we're going to look at the expectation and variance of this random variable. So, properties of the uniform distribution. Actually, maybe this is something you can tell me. Question for the audience, the answer should be, I believe the answer should be pretty straightforward. What is the expectation of this random variable? B minus A on 2, that's very close. That's not quite it, but it is very close. So the actual answer is A plus B. I think it's A plus B on 2. Yeah, because basically what you would expect the expected value to be is the point right in the middle here. Now, this point right in the middle, it's the average of A and B. And the average of A and B, you find that by adding the two numbers up and dividing by 2. So the actual expectation is A plus B on 2. But we don't just have to trust our intuition on this. We can actually do it the proper way, because the definition of expectation is this integral here, the integral from A up to B of x divided by B minus A. We all know how to integrate that. That's just a polynomial. We know how to integrate that. And it turns out the answer is A plus B on 2. Now, the next question is, what is the variance? This computation is much more involved, and I wouldn't necessarily expect you to be able to do it off the top of your heads. So I'll just tell you, by definition, well, by that property of variance we saw, it was the expectation of x squared minus the square of the expectation of x. More integrals to compute. You all have the tools to do this computation, but I've just done it for you. The answer is A minus B squared divided by 12. Now, I think this makes a lot of sense because what this is saying is that if A is really close to B, then all of the data is centered close to that point, A, which is close to B, and so we wouldn't expect the variance to be very high. On the other hand, if A is really far away from B, then this probability density function is pretty spread out. So we would expect the variance to be much larger. It turns out that the precise relationship is a quadratic relationship, and we've scaled by a factor of 12 because that's just how it works out. Okay. Now, the next one is a very important one that comes up a lot in real life. It's called the exponential distribution. I'll give you the definition and some properties, and then I'll try and explain to you why this is important. So the random variable x is said to have an exponential distribution if it's got this as its probability density function. Now, lambda needs to be greater than or equal to 0. Now, technically speaking, this isn't exactly the definition. The definition is f of x equals 0 if x is less than 0, and it equals lambda e to the minus lambda x if x is greater than or equal to 0. Because this is a random variable that lies on the positive real numbers, there's no chance of it being negative. Now, once we have the probability density function, we can simply integrate it to find the cumulative distribution function, and that's what we find. And you may notice that as x goes, well, once again, this, technically speaking, this is only defined if x is bigger than 0. And we can see that if x goes to plus infinity, f of x goes to 1, and everything works out. Okay. Now, you might want pictures of this. These are various graphs of a probability distribution function for the exponential distribution. For the purposes of this graph, a bit of a typo here. C is the same value of lambda that I was describing before. Now, properties of the properties of the exponential distribution. All right, what have we got? Well, basically just expectation and variance. But the reason I want to bring this up is because in order to actually compute these expectations and variances, you need to use some tricky integral techniques. So by definition, the expectation is the integral of the probability distribution function times x. So I've got to integrate x times lambda e to the minus lambda x dx equals 1 divided by lambda. Now, a quick question for the audience. Please put your answers in the chat if you know. How did I do this? How did I do this particular integral? No, the answer is I didn't just put it in Mathematica and asked it to do it for me, although that would be one option. If you did not have access to Mathematica, how would you actually work this out? I guess I'll refine my question a bit. What integral technique did I have to use in order to get this integral? Chain? No, it wasn't actually the chain rule. So no, it wasn't integration by substitution, and it wasn't the chain rule. But nice guess. I don't think the chain rule would help you in this one. Or maybe it would actually. maybe the chain rule would help. I'm not convinced. I'd have to try that myself. But the specific integral technique I was thinking of was integration by parts. Integration by parts is the thing that would do this for you, because what you would do is you would say that u is equal to x and v is equal to, well, v is equal to e to the minus lambda x, because then uv dash is just equal to x times e to the minus lambda x times minus lambda. And then when you replace this with u dash v, u dash is just 1. And so you're left to compute an integral of just an exponential. It's not an exponential multiplied by anything, just an exponential. Now that I think about it more, I am starting to convince myself that the chain rule wouldn't actually help. But yeah, I'm not 100% sure on that. At least not off the top of my head. Okay, now the variance, very similar. You have to do another integral, and this is another situation in which you do actually need to use integration by parts. Okay, now we've discussed the exponential distribution, and I think you actually came across, if I recall correctly, you did actually come across the exponential distribution in assignment 2, I think. You were asked to show, I think you were asked to show that this did actually integrate to 1 or something like that. Now, now I can explain to you why we made you do this. Oh, maybe it was the Poisson. Maybe you're right. Maybe I'm getting my distributions the wrong way around. But let me try and explain to you why the exponential distribution is important. It basically comes up anytime you ask the question, how long until something occurs? So let's say you're waiting for a particular event y to occur, and you're interested in the random variable x, which is how long until this actually happens. Now, more specifically, the exponential distribution is handy if you have the following assumption that's true for your event y. The probability that y occurs in a particular time interval doesn't depend on where that time interval is or how many times y has occurred previously. It only depends on how much time you're dealing with. So, for example, if you're interested in how likely it is that y will occur in the next minute, well, it doesn't matter when that minute occurs, it only matters that it's a minute long. So I was scratching my head trying to come up with a fun example of a real life situation in which this would be useful. One I came across was, maybe this assumption is a valid assumption when asking the following question: how long until insert band name, whatever your favorite musical group is, how long until they release their next song? Because maybe you might think it's a reasonable assumption to make that the probability that they release a song in a year, say, doesn't really matter on when that year is. It only matters that it's a year. Now, all of this may seem a bit silly and foreign to you, but I want to convince you that you probably will have thought about this kind of thing before. And the reason is because the exponential distribution of a random variable is basically just the continuous analog of a discrete random variable that you definitely would have thought about. And this discrete random variable is basically you do something over and over again, and you keep doing it until you get the outcome that you want. So, for example, if you keep tossing coins, the random variable x, which has the discrete analog of the exponential distribution, is if I keep tossing coins, how many coins do I need to toss until I get heads as my answer? So basically, the exponential distribution is the continuous analog of this particular experiment here. I did actually have more material prepared, but, well, this is probably a good place to finish it. It's been a long night. So yes, I'll finish there. I'll stop recording. Thanks very much for your participation, everyone. And I hope the quiz went all right for you. And I'll see you next week. Thanks, everyone.